Good morning, guys.
Morning.
Good morning.
Morning. Okay. So, did you guys try to do the questions at the back? Okay. It seems like it was a bit of a mouthful. Okay. Any questions, any concepts, anything that you had a hard time to figure out, or let's say it's okay, swallow.
89 and 91.
81, 89, and
91.
okay, let's just try to do those. Okay. First. 89. You said question 89, right?
Yep.
Good. Let's see what that one says. Now, what happens to the power in an ultrasound beam? Okay, let's see. What happens when the power in an ultrasound beam is unchanged and at the same time the beam area doubles? Clear. Now, most likely, it's okay. If you look at it, they're asking about, it's okay, the intensity. So we know that intensity was equal to power over area. Is that clear?
Yep.
Good. Now, what they say here, that, okay, yes. Okay, when the power in ultrasound beam is unchanged. So the power here is unchanged. Or we can say it's okay, is constant. But the area is doubled. Clear? Now, what do we know, my dear?
Yeah, I think I got it now.
Right, okay. All right. We can say that, okay, as intensity was directly proportional to
Power.
power. Okay, now since this is okay is not changing, or we says okay is constant. It's mainly as okay, just asking you, okay, what happens when you double the area? Okay, now we know that, okay, yes, that intensity is inversely proportional to area. Yeah, okay. Which mainly mean that you can that when intensity increases, that's when the area decreases, or vice versa. When the area increases, when the area increases, and here's okay, we can actually say that they're going to increase twice. That is going to mean that the intensity will decrease to the half.
Okay, that makes sense.
Clear? Okay. Now, although that's okay, they didn't put the word intensity in the question, but that's what they as okay would expect that you know will be as okay dependent upon these two things here. Okay, so pretty much okay is what we did when we establish these relationships here. That's mainly what they ask about. Did you get that, my dear?
Yep, thank you.
Good. And you said 91?
Yeah, it's kind of on the same idea, but can you just do it for practice purposes?
No problem, my dear. So we can say it's okay. Question number 91. Now, when the power of an acoustic beam is doubled, so we can say it's okay, the power is doubled, right? Okay. And the cross-sectional area of a beam is halved. Right, okay. Then the intensity of the beam is okay. Now we can do it this way. Let's just say that, okay, yes. Let's say this way. That we had a power. Let's say that our initial power, for instance, okay, is 4 watts per centimeter square. Clear? Okay. And we can take any area, just to not, that's okay, just to make it, that's okay. And not too complicated, we can say it's okay that we have an initial area of, let's say, 4 centimeters or 4 square centimeters. Okay. Now in this case here is okay, where is that our intensity is going to be? That will become, because it's okay, 4 watts per centimeter over square per 4 centimeters square. So we can make this okay, the intensity is 1. Now what is it that we do? We're going to double the power. So what we have was, okay, yes, we had 4 centimeters per, 4 watts per centimeter square, which is going to be doubled. So now our new power is going to be, okay, 8 watts per centimeter square. Okay, we had the area, which was 4 centimeters. Okay, which is, that's going to be halved. Which means that, okay, as we are ending up with an area of 2 centimeters square. And now you just do the math. Of the intensity is going to be 8 watts per centimeter square divided by 2 centimeters. Or 2 centimeters square. And what you get is 4 watts per centimeter square. So it actually is, okay, increased 4 times. Did that make sense?
Yep.
Right, okay. But even if you see here, it's okay, doubling the power is going to, it's okay, double the intensity, right? Because it's okay, the intensity is going to be doubled by, it's okay, doubling the power, because it's okay, they were directly proportional. Okay, whereas they do here is, well, okay, yes, they decrease the area. Clear? Okay, they decrease the area to half. But we know that, okay, decreasing the area is going to just, okay, increase the intensity by 2. Did that make sense? And that's a matter of, okay, yes, adding these 2 up. And it gives you, okay, what the change in the intensity would be. But theoretically or practically, yes, okay, if you want to just okay, calculate it out, yes, okay, you can just do it this way here. Did that make sense?
Yeah, I just figured
Yes, ma'am.
power, like it would just be the same as power, just because of, I was thinking in the sense of power, intensity, amplitude.
Okay.
But that makes sense.
Yeah. Okay. Not anybody else?
Question 100. I might be
Okay.
overthinking it, but it's like 100 through 104, and I'm pretty sure I'm
Okay.
overthinking them.
Let's see, my dear. Okay, so let's see. Answer the following 5 questions. Okay, so we have a statement. Okay, we have a statement. So we say it's okay that I'm going to be it's okay to sound pulses travel through the same medium. In same medium. Clear? Okay. Now just for a case, that's okay. What do you mean by same medium? Is going to be the same tissues, soft tissue, bone, whatever tissue you want to talk about. Yeah. Okay. Okay. Now we have 2 waves. We can say it's okay. Now we can just label it as okay. One is going to be as okay. One wave is going to have okay as a frequency of 2 megahertz. Yeah, okay. And we can say as okay, the second wave. Because we have 2 waves, right? Okay. Okay. Is 10 megahertz. Oh shit. What the hell? Is okay, second is okay, going 10 megahertz frequency. Now, my dear, that's the info that you have. And okay, yes, now they are asking us, okay. Okay. Now, which wave has a longer period? So these 2 waves here, A and B, or 1 and 2, sorry, has the greatest period. Okay. And of course, that's okay. You might have been all thinking it because you might mainly have been focusing on all this, which is not really information that you need to answer this question. You only need to just, okay, know the frequencies. So I know, yes, okay, where the relationship between frequency and period. They were inversely proportional. Now, when they ask me about the greatest period, that will mainly mean that you will look for the smallest period, lowest frequency. Did that make sense?
Yes.
Okay.
Yeah.
Good. Now the next thing is, okay, now 101.
Yeah.
Which pulse has the greatest wavelength or the greater wavelength? And again, guys, what do we need for wavelength? Well, okay, they said the same tissue, we could just assume, just for us, okay, the simplicity's sake, okay, that it is a soft tissue. Okay. Value is okay for 2. Frequency, because it means, okay, which of these 2 waves, the different frequencies will have the greatest wavelength. Is that what they're asking about? Okay, longest wavelength. So we have, okay, yes, 2 megahertz. That's going to just, okay, give us a frequency, okay, a wavelength of 0.77 millimeters. Clear, okay. Where, okay, yes, for the other one, wavelength, 15.4. Now, you mean it's okay, just divide that by 10 megahertz. Okay, but the wavelength that you get in this case is going to be 0.154. So this one here is the greatest wavelength.
Okay.
But you didn't even need to do this math because, okay, what we already had established was that, okay, wavelength, whether you look at the equation here or whether you just, okay, look at the simple relationship that we said, that wavelength is inversely proportional to frequency. So when you're looking at, so when they're asking us, okay, for the greatest wavelength, you may just, okay, just have to choose the lowest frequency. Did that make sense?
Yeah. Thank
Okay.
you.
So the math here, yes, okay, I just did. Okay. Good. Any other questions?
102.
102? Okay,
Yeah.
my dear, no problem. So what they're asking about in 102 is, which of these two waves here, 10 megahertz and 2 megahertz, has the lowest propagation speed? Clear?
Yeah.
Good. And that will be neither.
Is that because they're in the same tissue, they're in the same medium?
Exactly.
Okay, that's what I assumed. Okay.
Clear? Okay. 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 But it's because it's the same tissue or same medium. Okay, neither of them will be faster or neither of them will be slower. Mainly because, okay, if it's the same tissue, it's going to be, okay, the same speed. Did that make sense?
Yeah.
Okay. Any other question?
Yeah, my last one's 104.
104. OMG. So which pulse has a long, okay. Don't worry about that one yet, because, okay, we haven't done spatial pulse length yet. Okay, dear?
Okay.
Okay. That's probably, okay, something that we'll talk about in the next chapter. Or the upcoming chapter. Yeah, okay.
Yep.
So that's okay. Anybody else?
75.
Pump it up.
75.
75. Okay. 75. So the maximum density of an acoustic wave is 60 pounds per square inch. Okay. That's not the unit for density, but anyways. £60 per square inch. While the minimum density is, okay, is 20 pounds per square inch. What is the amplitude of the wave? Okay, guys. Now let's just take a wave. Is that clear? That's the wave. Clear? Okay. Now what they say is, okay, at the maximum density, because that's okay, it's going to be this. And minimum density. Let's just make it colorful. It's 20 power parts. Okay, guys. Now my question will be is, okay, what is going to be the number here? Or what is the middle number between 20 and 60?
Forty.
Huh?
40.
40. Yeah, okay. So, and what do you say the amplitude was going to be? Amplitude could be either this or amplitude could be either this. So whether you count from 40 to 20, right? Or whether you count from 40 to 60. Because, okay, what did we say the amplitude was? From the medium or from the average to the peak, or from the average to the minimum. Is that clear? And why is it that the SOK used density in this case here? Because means that, okay, as amplitude could be expressed in pressure, density, or particle motion or distance. Did that make sense?
Yes, so the 40 is just the average of the 60 and 20, correct?
Exactly.
Okay.
And then you can make it as, okay, now the difference between 40 to 60 is 20. So is the difference between 62, 40 to 20. Okay, what we mean is, okay, this here, if you look at the definition of amplitude, it means, okay, said from the average to the maximum or from the average to the minimum. Did that make sense?
Yes.
Yeah, okay. Anybody else with any other question?
Well, this may be silly, but one of the options or number 92, like the option was increase
92. Okay. Okay,
yeah, ninefold. Does that just mean 9 times? Never heard of
ninefold, yes. Now, when it
Alright.
says increases, it's going to be times.
They're really trying to trick us, huh?
Okay. Yes, guys. Anything else? Okay. So, what did you realize? That it's mainly as okay all about the relationships. If you got those, you should have no issues, at least for now. Okay, Kristen, you don't have any questions? You got everything?
Some of the questions I already asked were things that I had.
Okay.
So.
Okay, so somebody already asked them. Yes. Where were you, Jennifer? You good?
I think so. Hopefully.
Okay. Okay. What about you, Dr. Lillian?
I think I'm good for now. I guess
You-
we'll see.
We will see when.
I don't know. As I keep studying, I'm gonna go over the questions again and hopefully, like there were
Mhm.
some that I had to read the description for, but I'm hoping that next time I won't have to.
Okay. But which one were those that you had to read the description for? Because, okay, let me put it this way. A lot of the questions, not a lot, but it's okay. There are going to be, it's okay, some questions here that you may have to read 2-3 times to even try to figure out what the is it that they are asking.
I didn't mark them, but like if I was confused, like I would just read the description and it made sense to me after that.
Okay. But yes, okay, guys, these are questions that you probably, it's okay, what I would recommend is runningly. Just go back and try to answer them again. Try to answer them again. Try to answer them. Okay. But you will see for now, you feel that if I throw any of these questions in your head or face or on a piece of paper on the quiz, you'll be able to answer them without having to look at the descriptions.
Can we
Oops.
go over 119?
118, okay.
119?
118 or 119?
119.
119, okay. I can do 18 as well if you want to, but it's okay. Let's see. Now the propagation speed of okay. Okay, yeah, sorry. This one, because I what they're asking, okay. Okay. It's a duty factor. So we talk about duty factor in the next chapter there, okay? Okay. You don't know what a duty factor is. As a matter of fact, it's okay, you still don't know it's okay what it means to be a pulse wave. Okay. Any other question? No?
Just out of curiosity, would you like give us a question like 125? It was like the best estimate for the speed of sound in a tendon.
Now, as I told you guys, the specific speeds for the different tissues, except soft tissues, are not values that you need to know. Clear? Okay. But
Yeah.
but as I said, it's okay. Where is the least followed by higher, followed by higher, followed by higher, followed by higher? That sequence you will need to know. Did that make sense? Clear? Okay.
Yeah.
Now, A question can be tossed, or it's okay, be given, which says, okay, scanning 2 tissues. One lung, one liver. Now, what would you know from that? Now, lung is going to have a lower speed, liver is going to have a faster speed because you know the sequence. Clear? Okay. But then it can be as okay, a lot of okay, different rays, okay, weird things that can be popped in and say, okay, whatever is okay if you scan it with different frequency transducers, blah, blah, bleep, bleep, blue, blue. Clear? Okay. Did that make sense? Or we can say, okay, which tissue will we have a greater wavelength and which will we have a lower wavelength? Now that should be as okay obvious from the statement that I gave you that says that speed affects the wavelength. Okay, which you may as okay can see from the equation is going to be directly proportional. Okay, now in the equation that we have for SOK wavelength for SOK soft tissue 1.54, that was just taken from the speed of sound in soft tissues, right? But if it is going to be SOK a tissue with a greater speed, let's say boom, then you have to take the speed as 3,500 meters. Did that make sense?
Yep.
Yeah, so, okay. And if that is going to SOK be scanned by SOK the same transducer, well, okay, you will have a greater wavelength. Compared to SOK, a tissue scanned by the same transducer with a lower frequency. Not with a lower speed. Right, okay. So speed is directly proportional to the wavelength, but it's the speed that affects the wavelength and not the wavelength that affects the speed. Did that make sense? Yeah, okay. So a tissue with a greater speed will have a greater wavelength. A tissue with a lower speed will have a lower wavelength. Yeah, okay. Did that make any sense?
Yep.
If scanned by the same transducer. Baker says, okay, same transducer will be with same frequencies. Clear? Okay. Whereas if you scan the same tissue or medium, which is going to have, okay, a fixed speed with 2 different transducers, then the wavelength in that tissue is going to be inversely proportional to the frequency. Yeah. 2 different transducers, which you can say it's okay, different frequencies. Okay, but specifically as okay, what's going to be the sound of speed in a tendon? No, not necessarily. Okay, you can probably say, well, okay, 5,400. That's even not the speed of boom. Okay, so you can say, okay, that typical range or typical value, it was between 500 to 4,000. So you can say, okay, 5,400 is beyond that. It can be 1,000 meters per second because that is even slower than the that is even slower than the speed of sound in soft tissue, right? Clear? Okay. It can't be B as in boy because that was the speed of sound in soft tissue. So how do you answer? How do you get to the correct answer, which is that's okay, estimated? That's okay, 1,745 meters. Or 55, sorry, or 54, sorry. Meters per second. It's made as okay just by exclusion, right?
Yeah, that's how I did it. I was just curious
Exactly.
if we'd have
Exactly.
something like similar.
Yeah, okay. So even if you are, well, okay, yes, you can always just okay do the exclusion. Exclusion of what? That's okay. What I may have told you that also that's okay. You may need to. No. And that's why it's okay. It says okay, an estimate. Did that make sense? Good. Anything else? But when you get questions where it's okay, things will be given as okay, asked, estimated. Yes. Because there are things which we may not exactly know. Okay. You will see a lot of those estimate questions in chapter 9. I don't go to chapter 9 and look into that. Okay, but like okay, that's mainly it's okay, where it's okay, questions like okay, estimated, yes, okay, may start popping up. Okay. Anything else? Nope. Good. So let me just make up a question and see. Now, since you asked it, we can say it's okay. Two different medias. Are being scanned using a 5 megahertz frequency transducer. Now, one question that you should ask, can be asked, is which has the greatest wavelength? Which has the lowest propagation speed? Yes, guys.
Bone has the highest wavelength.
Bone has the highest wavelength. Okay.
Tendon has the lowest propagation speed.
Tendon has the lowest propagation speed. Exactly. Very good. Yeah, okay. So what the blue did I do here? You didn't really need to have this, right? Okay. This was just blah, blah, blah. But if we do it this way and say, and go like, you are scanning out. Let's say what's this? Okay, of soft tissue. Here we go. So
Is it-
what are you scanning? You're scanning a medium. Okay, and we say it's okay, this medium here is soft tissue. Clear? Okay, now what are we doing? We are using two different transducers, or respectively 5 and 10, 8 megahertz frequencies. Clear? Okay, now comes our questions. Now, which has the greatest wavelength?
5 megahertz?
Huh?
5 megahertz? Sorry, I'm losing my voice. 5?
5 megahertz. Okay, good. Exactly. Clear? Okay. So 5 megahertz. Okay, good. Which has the lowest propagation speed?
Same propagation.
They will be the same. Very good. Okay. And which has the greatest period?
5 megahertz.
5 megahertz. Why?
Because it's cycles per second, so 5 cycles. I don't know, this is how I do it in my head, but I kind of like draw it and it's gonna be longer. One cycle is gonna be longer.
Mhm.
So it's gonna take
But just
longer.
because, my dear, just because there were the 5 ones that also had the greatest wavelength. So wavelength, of course, that's okay, was going to be. Yes, it's okay, directly proportional to period. You can do it that way as well. Yeah, okay. But that's okay. Nobody forbids you. It's okay from draw. It's okay. A picture in your head. It's okay if it this yes, okay, was 1 second in your head. Well, okay, you will have 5 million cycles in 1 second for it to be 5 megahertz. But it's going to be even more cycles if you go by 8 megahertz per because then you have to have 8 million cycles in one period period of 1 second, right? Okay. But then okay, yes, okay, you will have a less shorter period, whereas here is okay, you will have a greater period. And since it's okay, you have a greater period, you will have a greater wavelength, and vice versa. Since you have a lower period, you will have a lower wavelength. But yes, okay, again, just establish that okay, yes, wavelength, yes, okay, is inversely proportional to frequency. Or the greater the wavelength, the lower the frequency. Lower wavelength, greater frequency.
Mike,
Yes, my dear.
you might want to punch me.
Why?
Can you can you go back to the first example? So the like slide before this one. I don't know. I'm just like maybe having a
Maybe
brain
I will
fart.
punch you then.
Oh, okay. So the greater wavelength is bone. Can you just explain why one more time?
Because, my dear, what did I say? No, my dear, it's not directly written in the book. It's written in between the lines. But what I mean, and that's why I gave it to you guys that, okay, yes, we can say that the speed of sound because it's okay affects the wavelength. Okay, now we can just put that into yes, okay, proportions and say an increase speed of sound will mean yes, okay, lead to an increase in the wavelength. Did that make sense?
Yes, thank you.
Or on the other hand, no, not thanks.
Okay.
Or on the other hand, we can say that okay, as a decrease in speed leads to yes, okay, a shorter wavelength. Did that make sense? Okay. Now what we know is that okay, yes, the speed of sound here is going to yes, okay, be determined by the medium, right?
Yep.
Yeah, okay. So this is pretty much okay. Well, all we can say is okay that the medium will affect the wavelength, which primarily as okay was produced by the transducer. Yeah, okay. So as a sound wave, yes, okay, leaves the transducer, it will have a certain wavelength which is determined by the period of the cycle produced by that transducer, which determines which is determined by the frequency of that transducer. Did you get that? But as that sound travels through the medium, the speed at which the sound travels through the different mediums will affect the wavelength. Did that make sense?
Yes.
Good. Yeah. Which we mainly as okay from our well-known equation that we say is okay, well, shit. The wavelength is going to be equal to is going to be equal to 1.54. Now, please keep in mind, my dear, this 1.54 here, which will be as okay, will be as okay in the unit of millimeters. This 1.54 is only applicable for soft tissues. Did that make sense?
Yep.
Okay. And when we talked about it, I say, it's okay, this 1.54 here mainly is just okay, because it's okay, derived from the speed of sound in that soft tissue. Is that clear?
Yes.
Good. Okay. And then, of course, that's okay. At the other end, yes, okay, we will divide that by the frequency, which you can mean as, okay, in this equation here, what is it that we have? That we mainly can say that, okay, yes, wavelength is going to be as, okay, directly proportional. Now, that's okay, here it says, okay, speed of sound in the tissue. Did that make sense? But it's also going to be as okay inversely proportional to the frequency. So what we mainly can say is okay, if we had a tissue where the speed of sound is, for instance, okay, greater than that of soft tissue. Okay, we can say as okay, for instance, okay, muscle. Let's just say that okay, the speed of sound in the muscle was okay as 2,500. That will mainly mean that the wavelength will be greater. Did that make sense? Because that's going to be affected by the speed of sound in that medium. And that's why we said that okay, as wavelength was not only as okay determined by the source, which is the transducer, but also as okay by the medium. But what is it that causes the medium to affect the wavelength is actually as okay the changing speed. Yeah. Whereas on the other hand, if we had a tissue or a medium in which is okay, the speed, for instance, okay, was less than 1,500 or 1,500 meters per second. Let's say there's something like lung variant or it's also 500 meters. That may mean that okay, as here, that will be the number that we will put into this equation and then divide it by the frequency. Where the frequency is mainly as okay, there's going to be what the frequency of the transducer was. Yeah, okay, so we can mainly as okay, based on this, say that in a medium where the sound is okay, maybe traveling at a greater speed, that will cause that, okay, that will lead to, as okay, that there will be an increase in the wavelength. Did you get that? Whereas if it says, okay, a sound wave travels in a tissue with a lower speed, that will cause a decrease in the wavelength. Did that make sense?
Yep.
Okay. And y is okay in the middle. That's okay. We had this number here. It's okay, 1.54. But this is only going to be applicable to, yes, okay, soft tissue. Okay, where did we get this 5? What's okay, 1.54? Tells me it's okay, derived from the speed of sound in the soft tissue. But if you go to faster tissues, you will replace this 1.54 here by just the number of the speed of sound in millimeters in that tissue. Or the other way around. Okay. But, the wavelength will not affect the speed. Okay. Which means, yes, okay, will just mean that, okay, why would the wavelength not affect the speed? Because that speed was determined by the source. Okay, where is it that the wavelength primarily is determined at by the transducer. How? All dependent upon what the frequency of that transducer is. So that's like saying, yes, okay, if the frequency cannot affect the speed, then so can the wavelength not affect the speed. So can the period of the sound wave not affect the speed. Did that make sense? Oh, that's more like the type of classes I want to have. You see, the more you ask, the more you learn.
Mike, I have a question.
Okay, so I'm not going to punch you in the face. Okay, go ahead, my dear. Yes, Jenny.
Oh, sorry, I didn't mean to cut you off.
No, okay, go ahead, yeah.
So quick question. So on the test, if you had like a question that was like, what is the relationship between power and amplitude? But power and amplitude are directly related only when amplitude is squared. So if you asked if power and amplitude were related and it didn't have the square at the end, would that be not related? Or
No, that will still be related.
that would still be related even if the square is
Yes,
not there?
even if the square is not there.
Okay. That was my question. Sorry.
Okay. The only thing about the squaring is that, okay, yes, we can say that the change in amplitude, has to be squared to determine how much change there will be in the power. Did that make sense?
Yes, thank you.
Okay, okay. But even if it wasn't squared, it is not going to be wrong to say that, because what does it mean to be directly proportional? That, okay, just because the amplitude increases, well, okay, the power will increase. Or the amplitude decreases, well, okay, then the power will decrease. And so, for instance, it's clear, okay? So just because it doesn't say amplitude square, it doesn't make it wrong, because it still says, well, okay, increase in one increases the other, decrease in one decreases the other. Clear?
Yes, thank you.
No problem, Jeff. Yes. Any questions? Okay. Now just chew on this thing here for 10 minutes and I'll be back and then we can, let's see, hopefully start on with the next chapter. Unless somebody say, okay, can you go back to the very first slide that we did? Okay, guys. So let's say it's okay. See you guys around 10, 15-ish. Before I go on, any questions?
No.
Nope. Good. Now, is that just from you, Kristen, or from all of the girls as well?
No questions here.
No questions either. Okay, good. Let's see how long that lasts. Okay, guys. So let's jump on to the next chapter, which is going to be chapter number 4. Okay. And what we will start talking about is going to be as okay, what we can call pulsed waves. Okay. Now, just be as okay, just say that, okay, what kind of waves? Sound waves. Did you guys get that?
So pulsed waves are just sound waves.
Now, waves here will be sound wave, right? Okay. Clear? Okay. So our main thing in this chapter is going to mean is okay, we are talking about, so what the do we mean by pulsed waves? Clear? Okay. Now, before getting into yes, okay, what a pulsed wave is, let me just draw a wave. And guys, that's okay. These waves here could continue out of the whiteboard, out of the room, through my backyard, through the neighbor's backyard, through his house, through his front yard, through the street, through the house across the street. Clear? Okay. So this wave here is okay, where there is, you can say it's okay, no stop of the waves. It's mainly going to be that, okay, that goes on continuously. So this is going to be as okay, what we call is okay, a continuous wave. Yeah, okay, and I can make this okay, just go on and on and on and on and on. Okay, guys. So that'll be as okay, what we call a continuous wave. Let's guess that's okay, go with a little impractical example, but that's okay, hopefully we'll explain it. If I go on and just keep on talking, no breaks, no breaths, nothing. Just go on from as okay. The time I'm born till the time I depart. my whole lifetime just go on and blah 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 blah. What will that be? You can say, okay, this dude here is continuously talking. Did that make sense? Yeah, okay. So what would that be? Yes, okay, we talked about it. We say it's okay, talking will be a wave. There's going to be continuously waves. Or continuous waves. Clear? Okay, where there's no stop, no breaks, no pauses, nothing. Just continuously blah blah blah. Did you guys get that? Okay. Now, just a little info that, okay, is going to get handy later on. Because, okay, we said, okay, this continuous wave here, okay, let's just. Okay, so it's okay, because it's okay. Let's do it this way, and we say it's okay. You said, okay, this here is okay, was continuous wave. Yeah, okay. Now, guys, this continuous wave here, okay, that is going to be as okay where we will produce by what we will call as okay non-imaging transducers. Is that clear? Okay. So a transducer that produces as okay what we can call as okay a continuous wave will be as okay considered to be a non-imaging transducer. Okay. What do we mean by as okay being non-imaging? What you can say is okay, what is going to be imaging? Will mean as okay, say as okay to produce an image. Or what we as okay, in this case is okay, we'll call it a scan image, right? Did that make sense?
Yeah.
Okay. But when we say it's okay, it's non. That mainly mean that okay, yes, a transducer which produces a continuous wave. Well, okay, it's still going to be a transducer. But it's okay, that transducer cannot be used to produce an image. Did that make sense? Okay, so this is okay, transducer which produces a continuous wave transducer can be known as a non-imaging transducer. We can also call it a therapeutic transducer. Or just because it produced just okay what we call a continuous wave, it can also just be called a continuous wave transducer. Did you guys get that?
Yeah.
Good. Okay. So one thing that okay is that a continuous wave transducer will not give you. Well, okay, yes, you can still use it, but it's not going to give you an image or a scan. Clear? Okay. So that kind of transducer, which produces a continuous wave, is going to be a non-imaging transducer. Mainly because, just as a transducer that produces a continuous wave, we can also call them continuous wave transducers. Okay. And some of you will say, well, okay, why in the hell do we need to know about this? Okay. Now, guys, later on, in chapter 19, when we get to that point, I can even give you guys a paper. Don't go and read on it now. It's guys going to flip your minds upside down. Okay. But that's going to be, as on page 313 is a fellow that's called the continuous wave transducer that we still will be using. The only thing is that, okay, he or she will not give us an image. But we're going to use her for other purposes. Clear? Okay. So for now, that's okay. Any transducer that does not, or that's okay, which produces a continuous wave. Wave with no breaks, no stop. Just cycle after cycle after cycle after cycle after cycle after cycle. But it can be called a continuous wave transducer. That continuous wave transducer can also be referred to as being a non-imaging transducer. Clear? Okay. And it can also be called a therapeutic transducer. Now, have some of you ever been, bothered by, ache in the shoulder, neck, or the back, or something like that? Okay. What could you do back in the days?
Ice it and heat it.
Heat it. Let's go with the heat. What is that the heat is?
What do you mean?
What is heat?
Like a warm pack?
Okay. What is heat?
Energy.
It's a form of energy, my dear. Did that make sense? Okay. Now that's okay. That heating pad, if you say, okay, I use a heating pad. What is that? Well, okay, that is going to be something that warms up and okay, but what is it that it will be doing then?
Producing energy?
It produces heat, right? Okay, and that heat is going to be transmitted from the heating pad onto the area where you placed it, right? And warm it up. Okay, now just look at a sound wave. What is a sound wave? Or what is sound?
Energy?
Energy. Clear? Okay, okay. Now that's okay. You may have those massaging guns. Not an AK-47 or something, but it's okay, a massaging gun. And what is it that do?
Uses energy.
It vibrates, right? Okay.
Mhm.
Okay, but that vibration is going to be as okay, you can say it's okay, transmitted from the gun to yes, okay, what area is okay. Yeah, okay. So the same as okay application is okay, maybe used here. Okay. That okay, as they use a transducer which continuously is okay, just transmit sound energy. Clear, okay. And which is well, okay, it's not going to produce an image. Well, it's okay, that energy is okay as it passes through the tissues is going to be converted into heat because it will be absorbed. And there's a continuous flow of sound wave, which produces a continuous, it's going to be okay, a continuous production of heat And that ultimately is okay, warm up your tissue, and you get the same effect as you got from the heating pad or whatever. Okay. All right. So in that sense, that's okay. It can be referred to as being a therapeutic transducer because they may use it for therapies. Okay. Physiotherapy and things like that. Did that make sense? Okay, but if there's one thing that you can't use these transducers to is to create an image. Is that clear? Okay, so they will not give you an image. They will give you something else, but okay, not an image. Did that make sense? So that was a continuous wave. This was a continuous wave transducer, which we also know as a non-imaging transducer and or a therapeutic transducer. Did I make myself clear on what a continuous wave is? Good, because now, since we have that in place, we can say, okay, what does it mean to be in pulses? What do we mean by okay, a pulsed wave? Yeah, okay, as a result of a pulsed wave, yes, okay, we may say, okay, a transducer that produces pulse waves is going to be a pulsed wave transducer, right? Clear? And okay, and that's why I say, okay, this thing is now going to look more and more and more and more ultrasound alike because what is it a pulsed wave transducer will give you? That will give you an image. Clear? So, contra. Let's just say it's okay that we had our continuous wave. And that was going to be as okay, if that was produced as okay by a transducer, we'll call that transducer as okay, a continuous wave transducer. We also call it the non-imaging transducer, and or that non-imaging transducer could also be referred to as a therapeutic transducer. But why mainly? It's okay because it produces what we call the continuous wave. Did you guys get that?
Yeah.
Good. So, guys, what we will have now is going to be as okay a transducer as well. Clear? Okay. And now we made it. And what we mainly is okay, we'll just say now is that okay, this fellow here is okay, he or she is going to is okay, be producing is okay, what we'll call a pulsed wave. So what is it that a pulsed wave is going to be? That is mainly as okay, going to be as okay, short bursts of cycles followed by a break. And we can say, okay, there would have been a burst of cycles followed by a break. That makes sense. So these here, this orange part here, that's going to be the pulsed wave. This is going to be the pulsed wave. Why? Because they were mainly as okay, what we can call as okay, as short as okay, we want to say burst of cycles or waves. Very common is okay, between is okay, a burst and burst. Is there going to be as okay, a break or a pause? Did that make sense? Now let's just go with the speaking example. Okay, well, let's say as okay, sound waves that are produced which you can hear. So what would it be to, or what would it mean to be as okay continuous? Let's put it this way, it's okay as long as the class is on. From 9 to 2. I would go on non-stop. Blah, 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 blah. Okay? No across 10 o'clock, or it's okay, around about 10 o'clock break. Clear? Okay. No breaks in between to take a breath. No breaks in between to go for lunch. Nothing. That would have been a continuous view. Did that make sense? Okay. And as a matter of fact, yes, okay, I'll be continuous in the sense that none of you will get the chance to put in a word. I'm not going to interrupt Mike. Let him speak. And okay, as I just went on from 9 to 2, 9 to 2, 9 to 2. No breaks, nothing. That was a continuous view. But if I go and say, well, okay, one topic, okay, let's take a break. Then we come back, then we go and say, okay, yes, okay, another topic, okay, let's take a break. Then I go as when you come back, okay, another topic, okay, class adjourned, see you tomorrow. But what did I do? I was, you can say, it's okay, discussing the topics in a pulsed manner. Did that make sense? Or even as okay, if I talk, I can go on non-stop. Okay. No breaks, nothing. But that will be a continuous wave. But as I say, well, okay, let me just speak in pulses. And I say, okay, 3 words, then a break. 3 words, then a break. 3 words, then a break. And just assume that each word is a cycle, for instance. That would have been an example of, you can say, okay, pulsed speech or pulsed speaking. Did that make sense? Okay, so what is it going? What's going to be? What's going to be the main difference between continuous versus pulsed is that, okay, in continuous, there's no breaks, no pauses, nothing. It just continues, blah, blah, blah. Whereas, okay, if I go in pulses, whether that is number of words, or number of sentences, or let's say paragraphs, or whatsoever, whereas, okay, between, okay, as a fixed number of other words, I take a short break, or between is okay, number of sentences is okay, I take a break. Bigger or smaller, we'll get to that. But at least that's okay, it's not continuous, that's okay, between number of cycles, there's a break, then it's another number of cycles, then a break, then a number of cycles, then a break. So those number of cycles that are being sent in as a group will be a pulse. Did you guys get that? Okay, so our imaging transducers, they are not going to be continuous. They're going to be impulses. Did that make sense? Okay, so what is it we now can call as, okay, this was a pulsed wave. Okay, but what would we call this whole thing here is, okay, we can say it's okay, this transducer here is okay. He or she will be as, okay, a pulsed wave transducer. Clear? Okay. And mainly because that's okay, obvious, okay, this pulsed wave here is okay, what he or she is going to be able to do is produce imaging. That's why, okay, that pulsed wave transducer can also be called, or can also be an imaging transducer. Did you guys get that?
Yeah.
Okay. So what is that we actually have in a pulsed wave? We had the actual pulse. And then we had just, okay, this time where there was no pulse produced. Just so we know that, okay, what the blue we are talking about, because that's okay. Here's going to be as okay. Because it's okay, another pulse. Now, guys, the time where it's okay, the transducer is producing what you call a pulse. That is going, that's okay, that will go under different terms. That's okay, we can call it the on time. Okay, it can also be called the talking time. Did you guys get that?
Yep.
Good. Whereas we can say it's okay, the time where the transducer isn't producing any wave because it was firing at pulses, is going to be as okay what we can call the off time. Okay. Now, what is it that the transducer actually is okay will be doing in this off time when it is not talking? It will be listening. Listening for what? For the sound wave that come back. Come back from where? From the tissues. Did that make sense? And what is that is going to do with those sound waves that comes back? That's what it's going to use to produce the, yes, Teresa?
The image.
Image, exactly. Or let us just use, just okay, we can say it's okay, or a class scenario. Let's put it this way, yes, okay, if I go on continuously from 9 to 2, okay, I might have warned you on day one that, okay, as there will be no breaks, no lunch break, nothing. So make sure that you have had your coffees, visited the toilets or restrooms or wherever you want to call it, had enough breakfast because you will now have, yes, okay, you will have to skip lunch. Clear? Okay. But even on top of that, yes, okay, I don't let any of you get any word in. Okay, I may be able to, yes, okay, speak out 2 chapters in a day. Clear? But if I don't, okay, and mainly it's okay because I continue to speak. And what is it going to happen then? Okay, as I may not give you guys the time to reflect back on what you might have learned or not learned. So if I want to draw a picture of, okay, how much did you get from the class that we just had? Would I be able to do so? If I don't let any of you say anything wise, that may, yes, okay, end up, yes, okay, make you earn $1 or an extra point. Oh, yes, okay, not so wise. Whichever. Well, at least that's okay. I get a reflection of something, right? An idea of, okay, what is going on inside your heads. But that's going to be impossible in the continuous view. Yeah. But if I say, it's okay, 5 sentences at a time, I say, okay, guys, any questions, any concerns? That's when I would zip and, okay, yes, hopefully it's okay, use my antennas to see if any sound is coming back. Anybody has anything to reflect, whether a question or that's okay, what they understood from what I said, or so on, so on, so. Clear? Okay. What that requires, okay, is I'm quiet. I stop talking and just listen. So what mainly happens in that off time, as we call it, the transducer does not produce sound waves. Clear? Did that make sense? Why? Mainly because, okay, it's giving that pulse that it produced time enough to travel and come back. Travel where? Into the patient's body and reflect information back. Did you guys get that? And it's going to be those reflections that the transducer then will convert back into what ultimately becomes the image. Now, since a continuous wave transducer doesn't have those breaks in between XYZ number of cycles, well, yes, even if there were reflections coming back, but they were going to be get silenced in the way. So are everybody clear about what it means to be continuous versus pulsed? And pretty much how this works. Now the further juicy details of all this that's what we'll be talking about for the next couple of weeks. Okay. So this one made is just the main info. Okay, now one thing that yes, you should be aware of, and that's I already gave it to you, is that questions may say continuous view. So what I hope that you'll be able to figure out from that is, there will be no image. Yeah. Okay. Whereas in this going to be in the pulsed wave that you have images. Okay. And why do we call it pulse? Because between a group of cycles and a group of cycles, there's a period of silence. Okay. That group of cycles together will be called the pulse. This group of cycles will be called the pulse. And in between them is what you call off time or a listening time. Where when the transducer speaks, or we can say produces sound, whatever number of cycles there's going to be in a pulse, we'll talk about that in just a little bit. Okay. But after I have said or produced certain sound waves, it keeps quiet. Then it produces sound waves, then it keeps quiet. Then it produces sound waves, then it keeps quiet. So the time that's when it produces sound, that's what we'll call the on time. Where when it's keep quiet, that's when it's not producing sound. So that's when it will be listening. Did I make myself clear on this? Okay. So right now, yes, as I'm speaking, well, if you were transducers, you were at the listening end. Now, if anybody will have anything to say, you are welcome to. Not even a thing like, we got it, Mike, get over it.
We got it, Mike.
Okay. We or you?
I mean, I for sure definitely understand the difference.
Okay.
We
Good. We. Okay. So I is we, and me is you. Have you guys seen that one? He is me and I am you. He is me and I am you.
Is that Jackie Chan? Chris Rock.
Yeah.
Was that
Rush
Rush Hour?
Okay, guys. So are you guys able to, so should we continue on to, let's say it's okay, the first parameter of pulsed wave? Okay, good. So, dear guys, the first parameter of pulsed wave is going to be as okay what we call the pulse duration. Yeah, okay. Now, what you just should get from the pulse, or the word pulse here, is that okay, as we are talking about, is going to yes, okay, be referring to what the,
Mike, this is a parameter, right?
you can put it this way,
Okay.
but you can say it will be yes, okay, a parameter of the pulse.
Got it. Thank you.
Okay, but if you look at it, just okay, it's pretty much going to just okay be closely related or linked or similar to a parameter of the sound wave. Yeah. So, but when we say it's okay pulse, what would this pulse here is okay refer to? Maybe it's okay just that number of cycles. Because that's okay. This is okay grouped together, right? Okay. Because it's okay, this here is okay, that's might have been the pulse. Okay. Because here's okay. This point here is okay, that was the start of the pulse. And we can say, okay, this point here is okay, what had been the end of the pulse, because after the end of the pulse is okay, this pulse is okay, the transducer most likely had gone silent. Did that make sense?
Yeah.
Good. Okay. Now, just look at the word duration. What do you get from the word duration? It's going to be as okay, the length in terms of time. Now, let me just give you guys, okay, it may be as okay, an obsolete example. Not necessarily. If you say, well, okay, there's a new movie on in the picture house or cinema, let's go and watch it. Okay, you as okay are going with your better half, and okay, let's say it's okay, the children. I said, let's have a movie night outside. Okay, probably one of the things that you will check on before is okay, saying okay, we should watch this movie, that movie is okay, that is not R-rated or something. Okay. That's going to be okay. A PG movie, right? Okay. Regular, okay. What do you call it? U-rated or something like that? Everybody can watch it. Anyways, clear? Okay. The next thing you say, well, okay, how long is this movie? Is that a movie that's going to just, okay, take forever to finish and you're going to doze off in the movie theater and not know what the movie happened because it got too long? So you will look at, okay, what they will refer to as the duration, right? Okay, nowadays they don't make, okay, those super long movies unless you're watching some Star Wars or something. Okay, usually 1 hour, 30 minutes, 145 or something. That's okay as the, you can say, okay, average duration of a movie. But that's going to tell you that, okay, as this movie here is going to just, okay, be running for 1 hour and 45 minutes, for instance. Okay, that's the duration of the movie. That's going to be as, okay, the time that it will take from the start of the movie to the end of the movie. Okay, but you say, okay, that's too long of a movie. You don't measure it in meters. You don't measure it in frequencies or anything. You measure it in time. So what is going to be the pulse duration? It's just going to be as, okay, the time that, because that's okay, it takes a pulse. Now, just to be more specific, that's okay, from the start of the pulse that's okay to the end of the pulse. Yeah. So what does that tell you guys? That, okay, yes, if this here is, okay, was our pulse. Clear, okay. If this here was the pulse, and this was the start of the pulse, this here, for instance, okay, was the end of the pulse, because after that is, okay, we'll go into, yes, okay, off mode. Then when we actually is, okay, measured the time from this point here to this point here. That will be, yes, okay, what we call the pulse duration, but it's measuring it in time. Did you guys get that? So if I'm talking and you're sitting there with, let's say it's okay with your stopwatch and recording the time during which I'm talking. And if I'm talking in pulses. And I say, well, okay, I'm going to speak for 5 seconds at a time and then take a break of XYZ amount of time. Then 5 seconds, then a break, then 5 seconds, then a break. Now, what would that 5 second be? That will be the time during which I am speaking, or me being a transducer, producing the cycles. Clear? Okay. Or we can say, as okay, that will be the period of your pulse. The reason I don't want you to use the word period for pulse is period was specifically as okay, just for one cycle. Okay. So for a cycle, okay, okay. If you talk about, okay, that time for one cycle, we call that a period. Okay. Okay. So what you need for a pulse is going to be 2, 3, 4, 5, 6, more than just one cycle. Okay. But the time that it takes that number of cycles that comes within a pulse to be completed will be referred to as the pulse duration. Just like the duration of your movie that you're watching. Did that make sense? Any questions? Okay, guys, just give me 1 minute, okay? I'll be right back. Okay. So what we mainly said was that, okay, yes, the pulse duration, that's going to be the time from the beginning of a pulse to the end of a pulse. Clear? Okay, and what remains is, okay, we have after the end of the pulse is going to be the off time. Did that make sense? Okay. And what this pulse duration here actually is going to be equal to is what we earlier, okay, said, okay, yes, the talking time, or what we refer to as the on time. Clear? Okay. On time or talking time of the transducer. Yeah, okay. But if you want to put it that way, that's going to be as okay, the period of the pulse. But the reason that try not to use the word period because period was meaning as okay, that's the time for one cycle. Okay, where we said that a pulse that was going to be as okay 2, or we says again more than 2 cycles. Okay, but of course that's okay. There is going to be as okay an upper limit because otherwise it would end up as okay being as okay a continuous wave. Okay. But what we can say the period and duration have in common is that they both are measuring the time for different entities. Period was for one cycle. Pulse duration was for 2 or more than 2 cycles, because once you have, you can say that one cycle with another cycle, this is already a pulse. We can add another cycle onto it. We can add another cycle onto it. We can add another cycle onto it. Did that make sense? Okay. But since it, yes, okay, talks of the time, it's going to, yes, okay, be measured using the unit of time, which is mainly as okay what we have talked about so far. Could be as okay a second. It could be as okay a multiple of a second. Probably not something that we will see in ultrasound. Clear? Okay. Mainly because okay, the typical values for this one is still going to be as okay in small fractions of a second. Did you guys get that?
Yes.
Okay. So just the time for which I've been talking in short bursts at a time would be what we call the pulse duration. Here I just spoke in pulses, right? Okay. I could have said that, yes, okay, continuously as well, right? Yeah, okay, those same words could have been said continuously with no break, no pauses, nothing. Clear? Did you guys get that? Right, okay. Now, the typical value. The typical value for a pulse. And guys, it's okay when we talk about it's okay, the typical value of a pulse, I mean, it's okay. I mean, it's okay, B, it's okay. Of pulse. Or what kind of pulse? Mainly it's okay for from an imaging transducer. Okay. Now, as we know that, okay, yes, of the pulse ratio is okay. This value here is okay, or is okay. It's going to be expressed in the unit of time. Or using as okay the unit of time. Otherwise, it would just have been a number. Okay. So the typical value is going to be as okay 0.2. What's that? 0.3, sorry. Microseconds. We can say it's okay, that's going to be the shortest pulse. 2 up to something like a 2 microseconds. Yeah, okay, now please keep in mind that, okay, yes, this 0.3 microsecond is okay. The 0.3 can still be written as 0.3. We can say it's okay that the micro here will be as okay 10 raised to the power minus 6. And yes, okay. The second will still be a second. Yeah, the same as okay, just apply over here. And we can say it's okay. 2 will still be 2. Well, okay, the micro is still 10 raised to the power minus 6. And okay, yes, your second is still the second. Did you guys get that?
Yes.
Yeah, okay. If you say, well, okay, I don't want you to write things in decimal, well, okay, you can convert this 3 here into a whole. Well, that is okay. You exponent over here is just going to change from minus 6 to minus 7. Okay, because 0.3 is still a fraction of that microsecond. Okay. And okay, guys, this typical value here. Remember it. Okay. So 0.3 microseconds to 2 microseconds. That's the typical value of an ultrasound pulsed wave, okay, which was going to be made up of a certain number of cycles. Okay, if you just check this pulses, okay, we have one cycle, we have two cycles, and we can say, it's okay, we have, okay, yes, 3 cycles in this pulsar. Now, the next thing that we will talk about, okay, is what is going to determine the pulse duration of the ultrasound pulse. Now, guys, just look at it in this way. We said, okay, yes, we had 2 things, right? Okay, we had the transducer, which we also call, yes, okay, called the source. And what else did we had that could determine things? Was, okay, yes, the medium. Did that make sense? Okay, but easy to remember is, okay, what determines your pulse duration. Is mainly going to be, yes, okay, just look at, okay, what are going to be the 2 factors that will determine the pulse duration, or yes, okay, make up the pulse duration. What is going to be is, okay, the number of cycles in the pulse. Okay, now these number of cycles in the pulse, yes, okay, are going to be wholly and solely, yes, okay, determined by the source and or the transducer. The other thing would be what we call is, okay, the period. And what we mean by the period, we can be more specific as the period of a cycle. And that period of the cycle was also, yes, okay, if you remember from chapter 3, was also, yes, okay, just determined by the transducer. So that's why your pulse duration is going to be determined only and only by the source. Why? Because it's mainly going to be, as okay, determined by, as okay, because it's okay, be dependent upon a factor here, which was the period of each cycle that was determined by the transducer. Okay. Likewise, okay, for this specific transducer here, it's okay, not only is the period of each cycle going to be, as okay, determined by the transducer, but for this specific transducer here, is okay, it may have, okay, as a fixed number of cycles that it will produce or have in each pulse that it makes. Okay, where we can mean says, okay, here in this case is, okay, we had 4 cycles in the pulse. That was determined by the transducer. Okay, but on top of that, we can say, it's okay, even this factor here, which is going to be, was going to be the period for each of these cycles here, also was determined by the transducer. But mainly because of the period here is okay, that's we can say it's okay that your pulse duration is determined by the source. Did you guys get that? Okay. Now, is this here adjustable? No. And the cheat is just to remember, guys, just like your period was not adjustable. Just as your period of each cycle was not adjustable, so is the pulse duration not adjustable for a transducer. Yeah, okay. Even that pulse duration for a transducer is not adjustable. So it will remain constant. Clear? Did that make sense? Just like, put it this way, it takes me 3 seconds to produce a pulse of saying it's okay 5 words at a time. Clear? Okay. That's how I said it. I spoke those 5 words in 3 seconds. That was my pulse. That's how I'm programmed. Yeah. Okay. So that was all that's okay determined by that. You guys can't change my program now. You can't update my software. I'm probably too old for that. Right? Okay. Okay. But so yes, okay, that's just how I speak. That's just how it's okay I communicate in pulses of 5 words in a cycle at a time. Of course, that's okay just with a shorter or longer break. Did you guys get that? So your pulse duration, guys, remains constant for a specific transducer. You want to change the pulse duration? Go ahead, get a new transducer. Clear? Okay. Now that transducer may have, okay, as a shorter or longer pulse duration. Clear? Okay. It may be as, okay, let's say it's okay having a shorter pulse duration. But it may just be as okay doing as I was, speaking 5 words at a time. Where you mainly will say about, okay, 5 cycles in a pulse, right? Clear? Okay. But why is it that that new transducer will have a shorter pulse duration? Mainly because he or she took lesser time to utter each word. Did that make sense? Or he or she might as okay have a pulse duration which was greater than mine, although it's okay, it's just 5 words per pulse, followed by a greater or shorter break. But that's just because that person then will speak or take more time to utter or speak each word. Did you guys get that? Clear? Okay. So when I'm speaking in pulses, the breaks in between is to give you guys the time to just, okay, receive the word, process them here, and okay, let's come back with a respond. Or even, yes, okay, you can speak. Clear? Any questions? So what was a pulse duration? Yes, okay, we can define it in different ways. You can say it's okay, it's the time from the beginning of a pulse to the end of a pulse. Clear? Okay. Or you can say it's okay, either the time or the duration of the on time or the duration of talking time. Clear? Okay. Which was mainly as okay, what happened during on time, what happened during talking time. That was when the transducer was sending out that bursts of pulses at the time that it takes to produce that pulse, which then is sent on a greater or shorter journey. Did you guys get that? If we measure it in a unit of time, because it is a time, it means, okay, how long does it take? How long, not in terms of distance, not in terms of intensity or something like that, but how much time does it take for the system, or in this case, it's okay, or a transducer, to produce a pulse. What's going to make up that pulse? A certain number of cycles. Did that make sense? Okay. So it will be dependent upon is okay, the number of cycles that we have in that pulse. But we can make this, okay, the main thing that will determine what determines the pulse duration will be the transducer, because the transducer determines the period of each cycle, which ultimately will determine the duration of the pulse, or the pulse duration. And just like we can't adjust the period for each cycle, hence we will not be able to adjust the pulse duration. Did you guys get that?
Yep.
Good. So what comes next? Let's talk about, okay, how do we calculate a pulse duration? Well, we can mainly say, okay, what is going to, okay, okay, make up our pulse duration? It's going to be, okay, the result of two factors. Let me just go to another slide, guys. That's so we can say it's okay. The pulse duration Now that's going to be as okay the product of two factors. And what is it that those two factors are? It's going to be as okay the number of cycles. Just to be specific, we can say it's okay number of cycles in the pulse. And the other factor is going to be, it's okay, the period. Now, just when we say period, it's okay to be more specific. What do we mean by period of each cycle? Did you guys get that?
Yeah.
So mathematically, my guys, this is how we calculate the pulse duration. Now we can take a pulse and says, okay, in this pulse says, okay, we have this many cycles here. Yeah, okay, we can just count them and say, it's okay, that's a total of 1, 2, 3, 4 cycles. Yeah, okay. And this totaling is okay from here to here is okay. That made our pulse. Yeah, okay. But we actually is okay, want to find okay as our is the duration of this pulse when we measure it in time. And that will mainly as okay be dependent as okay, what is the period for each of the cycles that we have. Okay, now in this case, yes, okay, we can say it's okay that the period for each cycle is okay, have to be the same. We can just say that, okay, yes, there was 2, or that says, okay, 0.2 microseconds. Now we can just get, okay, get the pulse duration done. Yep. It's going to be, okay, how many cycles did we had? We had 4. And we mean is, okay, just to multiply that 4 by 0.2. Which means, okay, just gives us a total of 0.8. And we just copy and paste the unit. Microsecond. Did you guys get that?
Yes.
Now, just another example where we may take another pulse. And what I just want you to do here is, oh shit. Say it's okay, because where if we, for instance, increase the number of cycles per pulse from 4 to 3, 5, 6, 7. Let's say we have 1, 2, 3, 4, 5, 6, 7, 8. So now I have, yes, 8 cycles in a pulse. Okay. Just to just says how is that the number of cycles will be just related to the pulse duration. In this instance, says we just keep the period the same. So it's still 0.2 microseconds. But for this pulse here is okay. So from here to here. What's going to be as okay, or new pulse duration? It's mainly as okay when we multiply that number of the cycles that we had in the pulse by the period of each pulse, or each cycle, sorry. And what you will see here is that, okay, our pulse duration is going to be as okay. Okay. 1.6 microseconds. Did you guys get that?
Yeah.
Good. Now, likewise, it's okay. On the other hand, now we can just keep this okay. Say that we use this example, but that we, okay, yes. If yes, okay, increase the period from 2 microseconds to, let's say, 4 microseconds. Now, if, okay, now what is going to be is, okay, our new pulse duration. If we increase the period, all this, okay, we kept just 4 cycles. Probably is in the cycle. Also, cycles in the pulse, sorry. Okay. So we said, okay, as we had 4 cycles, but when we increase the period of each cycle from 4, from 2 microseconds, 0.2 microseconds, let's say it's okay. We can go and say it's okay, 0.4 microseconds. That's okay. That's okay. So what do we have? That will be a total of 1.6 microseconds. So what did that tell you? That your pulse duration, that's going to be as okay, directly proportional to the number of cycles per pulse. Okay, because what we saw was that is okay, when we increase the number of the cycles in the pulse, what happened to our pulse duration? It increased. For the first example, that's okay, from 0.8 microseconds to 1.6 microseconds. Clear? Which means yes, okay, will mean that okay, yes, it will be greater. Whereas okay, where we had a lesser number of cycles in the pulse, that's okay, we had a shorter pulse duration. Clear? Okay. So yes, okay, we can say it's okay. Increase of the number of cycles will increase the pulse duration. Decrease of the number of cycles will decrease the pulse duration. Which means yes, okay, just is because that that these two factors here is okay were directly proportional. Did you guys get that?
Yeah.
Good. Now what we then also can say is that this pulse duration here okay, what was the other factor? Was period. And yes, okay, it was also going to be directly proportional to the period. Because what we saw was that okay, when we had a shorter period, we had a shorter pulse duration. Okay. we increase the period, we end up with a greater pulse duration. So that means, okay, just makes that, okay, as likewise, its period directly proportional to the pulse duration. Did you guys get that?
Yes.
Get now we can just look at this one here and say, well, okay, there was something there, for instance, okay, was inversely proportional to period, which was frequency. So since frequency is inversely proportional to period, frequency of a cycle, or let's say it's okay, of a pulse, is going to be inversely proportional to the pulse duration.
Can you say that again?
Period is inversely proportional to frequency, right? We know that from by now, okay, dear? Right?
Yes.
Good. So since period and frequency are inversely proportional to one another, and period and pulse duration are directly proportional to one another, that just makes pulse duration and frequency inversely proportional. So we can actually say that, okay, yes, your pulse duration, it is inversely proportional to frequency. That's sound wave, which mean that, okay, yes, the greater the frequency, the shorter the pulse duration, and vice versa. Lower frequency, greater pulse duration. Why? Because that lower frequency will have a greater period, which will increase the pulse duration. Or a sound wave with a high frequency will have a low period, which will reduce, or okay, cause you to have a lower pulse duration. That makes sense.
Yes.
Just a similar kind of relationship that we established between period and frequency and wavelength. Okay, but here it's okay. Did that make sense? It's the same concept of, okay, as copy and pasting. So, okay, two factors here are directly proportional, but one of these factors here is going to be inversely proportional to something else. So what will be the relationship of this one here to that something else? Right? Okay, or you can go this way and say, well, okay, period and pulse duration were directly proportional, but period and frequency were inversely proportional. Not only inversely proportional, they were also reciprocal. But that just says, okay, that inversely proportional, that would be enough for us. for now. Okay. So frequency will actually is okay, not only be inversely proportional to the period, but it will also be inversely proportional to the pulse duration, which will directly proportional to the period. Or you want to put it this way. My friend's enemy is my enemy. And my friend's friend is my friend. Did that make any sense? But then we can go and say, it's okay, is there anybody who will be able to tell me what is going to be the relationship between pulse duration and amplitude?
Directly.
Is it unrelated?
Huh?
Unrelated?
Unrelated. Why? Because nothing that plays a role in the pulse duration is related to the intensity. Or amplitude or power for that sake. Clear? Okay. So that's okay, they will be unrelated. So it's okay. If you guys don't have this, it's okay. Well, okay, you don't need to write down. Everything is written in your book. So what could be, it's okay, a question that you can be asked. It's okay, you have two transducer with two frequencies. 12 megahertz versus, let's say it's okay, 6 megahertz. Right? Right? Now they may ask, yes, okay, which will have, yes, okay, the greatest pulse duration, which will have, yes, okay, the lowest pulse duration. Now the pulse duration is going to be lowest for the one with the 12 megahertz and greatest for the one with the 6 megahertz. Why? This high frequency is okay, produces a shorter period. Clear? Okay. This high frequency transducer here will produce as okay sound wave with shorter periods. And those shorter periods of each cycle will cause a shorter pulse duration. Or on the other hand, this frequency here is okay, a low frequency, right? Okay. Will produce a greater period And that greater period will produce a greater pulse duration. That's pretty much okay as the logic behind it. So that's okay. If you thought that okay, as you were done with chapter 3 and okay, as finished, forget it. You may have second thoughts now. Okay, it's finished, but you can't forget it, okay? Okay. Okay, guys. That's fine. Just chew on this one here in between is okay, your bites. And okay, as when we come back, we can still talk a little bit more of okay, as more factors and facts about the pulse duration. Okay, guys. Okay. So I will see you guys no later than 12:40.
Long pause, Mike. Big break in your pulse.
Okay. So do you expect another number to come after 40?
I was waiting. I don't know.
40:10.
50?
Yeah.
Okay. Okay.
See you guys then. So what's the buzz? What about the pulses now? Any questions yet? Okay. Good.
Can I ask one clarifying?
You can ask not just one, you can ask as many as you want to do.
Thank you. Um, since period and frequency are reciprocal, pulse duration wouldn't be reciprocal with frequency, right?
No.
Okay, just making sure.
Okay. Okay. That's just because you can say, well, okay, yes. If it says, okay, let's say, okay, that the period was, let's say 20 seconds. But I do the opposite. Let's say it this way again. Let's say that, okay, we had, now be careful about the wording now because we says, okay, period is, let's say it's okay, 2 milliseconds. Yeah, okay. For this, now this is going to be as okay of one cycle. Okay, but what we get from this period of 2 milliseconds is going to be as okay a frequency of 2 half a kilohertz. Or we can say as okay 500 hertz. Okay, and it's when we as okay multiply. Let's okay. This half here. By this 2. That you get 1.
Right.
But that's going to be the period of each cycle. Clear? Okay. Okay. Now your pulse duration based on this then going to be as okay. How many cycles do you have in that pulse? Clear? Okay. That could be any number. Let's just say it's okay that we had 5 cycles. So now your pulse duration, my idea is okay. That becomes 2, sorry, that's going to be as okay, become 10 milliseconds. Yeah, okay. But your 10 milliseconds, okay, will be as okay, inversely proportional to as okay, your frequency. Because okay, when we find this, okay, either increase the period or decrease the period, that will cause a reciprocal increase or decrease in the frequency, but not in the pulse duration. Did that make sense?
Yep, thank you.
So if we find just okay, let's just say that we doubled the period here to, let's say it's okay, 4 milliseconds. Now I mean, call that okay as our frequency now is going to be as okay. Because it's like a 0.25 kilohertz or quarter of a kilohertz, which is going to be as okay 250 hertz. Okay. Clear. Okay. Now, with the same number of cycles, that's okay. Well, okay, as we have 5 cycles. So we can make this okay. Now the period is going to be, sorry, pulse duration is going to be 20 milliseconds. Okay. But it's only going to be the period that was reciprocal to the frequency. Only reciprocal. Okay. As far as okay, the relationship between pulse duration and frequency is concerned, yes, okay. They will be just inversely proportional. They will not be reciprocal. Did you get that there?
Yes.
So only reversely proportional as far as okay, the period of pulse duration and frequency of the wave is considered. Because you just okay, let's say it's okay, a low frequency, what do we end up having? A great a higher period, okay, which will lead to a higher pulse duration, or vice versa. Okay. A great frequency will lead to a shorter period, which will cause the pulse duration to be shorter. Okay. Provided that, okay, as we kept the number of cycles and the pulse constant. Did you get that?
Yes.
Okay. So our relationship between, yes, okay, where there was period, pulse duration to the number of cycles, pulse duration to the period, and since period is inversely proportional, let's just take only the inversely proportional thing here. That's how it's okay. Frequency and pulse duration also are going to be inversely proportional to one another. Did that make sense?
Yep.
Okay, but please, guys, okay, Don't confuse as okay the number of cycles here with frequency. Because frequency, after all, yes, okay, is going to yes, okay, what will be, what which means yes, okay, the number of cycles in a second. Okay, so that is mainly as okay, something which is completely different from the number of cycles in a pulse. Clear? Okay, so you can have a cycle with a great number, or you can have a pulse with, let's say, it's okay, a great number of cycles in it, but still a or a low frequency or a high frequency. So those two things are not related to one another. Yeah. So the number of cycles per pulse is not related to the frequency. Clear? It's going to be the period of each of those cycles in the pulse that's going to be inversely related to the frequency. The period of each cycle in the pulse will be inversely related to the frequency. Not only inversely related, but that's okay, actually reciprocal. Yeah, okay. But the number of cycles in a pulse is a completely different entity. Okay. So you can have a pulse with a great number of cycles. Okay. In that pulse, but still have a low frequency. Or that pulse can still, as okay, be a great number of cycles with a high frequency. Okay, that high and low frequency is mainly as okay, just going to be determined what is the period of each cycle in the pulse. You guys get that? Okay. So yes, okay, guys, it is after all, it's okay, just the relationships. Now, guys, when we said a pulse, because it's okay, the pulse duration. Okay. Because it's okay, this duration here is okay, is going to be as okay, directly proportional to is okay, primary is okay, the period. Now another thing would be as okay, the number of cycles in a pulse. Okay. And that okay, as we can say, okay, that will have okay as a typical range. Okay. Now different texts may say different things. What your book says is okay that the normal range of cycles in a pulse is anything between 2 to 4. All that mean that you can have cycles, also you can have pulses. Where okay, as the number of cycles may be as low as just 2. 1 pulse or 1 cycle, 2 cycle. You can have a pulse where the number of cycles is 1, 2, and 3. Or you can have, okay, as a cycle, or you can have a pulse with 1, 2, 3, 4 cycles in a pulse. Clear? Okay. Did that make sense? Okay. Some books or some literature may even, yes, okay, say anything between 2 to 6 cycles. Okay. And maybe as okay, at a later point, you may as okay come across an article that says okay, up to 10 cycles. Is that clear?
Yeah.
But okay, but then as okay, whether it was okay as this pulse here E, where we just had 2 cycles, or we can say okay, pulse B, where we had okay as a total of 3 cycles, or where we can say okay, pulse C, where we had okay as a number of a total of 4 cycles that made up the pulse. Clear? Okay. Now, guys, that just say that that's okay, provided that each of these cycles here had a period or whatever. We can say it's okay, 0.1 microsecond, for instance. So what would be as okay, or pulse duration for each pulse here? And we kept that as okay, the period for each cycle constant. For A, it was going to okay, be a total of 0.2 microseconds. Here it was going to be 3 microseconds. Here it was going to be 0.4 microseconds. Yeah, okay. There, okay, yes. But the microsecond mainly as okay, as of a period would actually as okay mean that in all the 3 cases as okay, the frequency of A, B, and C are still going to be the same because the periods were the same, which would be as okay 1 megahertz. Oh, sorry, 10 megahertz. Okay. So for all these 3 pulses here, the frequency will still be the same. Because what that will mainly mean is, okay, now here, our pulse duration was only as, okay, 0.2 microseconds. But which mainly will mean is, okay, had this pulse here has, okay, been lasting for a second, that would have been a total of 10 million cycles completed. Likewise for this one here. Okay, now although it's okay, it is only as, okay, 0.3 of a microsecond. But had this pulse here has, okay, been continuing, while these cycles has, okay, be continuing for a second, that would have been a total of, still would have been a total of 10 million cycles. And so for this one here. Clear? Okay. Where this number of cycles here is okay, can increase or decrease. Or the frequency is okay, it could either increase or decrease. If the reciprocally is okay, decreased or increased the period. So if you find this okay, said that our period was, let's say, 0.2 microseconds. Okay. In that instance, would the frequency then be 5 megahertz? Where we can then say, okay, what will be our pulse durations then? Now our new pulse durations with this new period here will be 0.4 microseconds. Zero 0.6 microseconds and 0.8 microseconds. Sorry. Clear? Did that make sense? Okay. Did you guys get that? Which made or meant that, okay, yes, with this period here, it's okay, if it had continued on for 1 second in either of these waves here, or in either of these pulses here, it's okay, you would still have had 5 million cycles in a second being completed. Did you guys get that?
Yep.
You said no?
I said, yep, my nose is just stuffy. I'm sorry.
Okay. So a yo is a no. And a ness is a yes. Okay, guys, is there anybody who is still confused? Or did it just make you more confused than you already were? Guys, I don't mind. If you didn't get it, let me know, guys. I have no problem. Oh, the problem is, okay, I just have to go over it again. That's what. But that's not the biggest issue here. The biggest issue is, okay, is if you don't let me know that you didn't get it.
I think I got it.
You think you got it? Okay. Okay, guys, now then let's just say it this way. Well, the next question will be is, okay, out of, let's say, this pulse here with less is, okay, 2 cycles. let's say it's okay, this pulse here with 3 cycles. Well, let's say it's okay, this pulse here with 4 cycles. Now, please keep in mind that, okay, for this example here, it's okay, you will say a period is constant, right? Okay, that's the same. All three of them. Let's say it's okay, 0.2 microseconds. Okay, which means okay will give us okay as a frequency of 5 megahertz.
So we'd be given the period and frequency.
But okay, if it's relevant.
Okay.
If I say, well, okay, what's the pulse duration for this pulse here? You had 2 cycles. If you don't know what the period of each cycle is, you have no clue, right?
Right.
Right? If
Yeah.
I give you a question and say, it's okay, everybody is going to bring in 4 candies. How many candies will we have at the end of the day? You don't know how many people I'm talking about, right? It could be just 2 people, it could be 20 people, or it could be 2,000 people. How would you know? Did that make sense?
Yeah.
Just like as okay, earlier we had intensity. Okay, or they didn't. The question could have been worded a little bit better. But anyways, okay, okay. My gain is okay. You say okay. I had a power. I had a area. So that should be as okay. Yes, I understood. Or at least again. Yes. Okay. Okay. So out of these pulses here, now it's okay. We just kept these things here constant. Okay, we say okay. The period of each cycle was the same. Of course, that's okay. The pulse duration of each cycle or each pulse, sorry. But okay, it will not be the same because in one we had 2 cycles, and one we had 3 cycles, and one we had 4 cycles, and you can go on like that. But we made as okay, so now which of these 4 cycles or 3 cycles here is going to be best? We can say it's okay, good. Or let's say it's okay, worst. Or diagnostic imaging. Now, guys, the main thing is going to be that shorter pulse is best. Long pulse would be as good. And we can say it's okay, the longest pulse would be the worst. For diagnostic imaging. Did you guys get that?
Yep.
Yep.
Yeah, okay. So if we had, okay, as these 3 pulses here, okay, of course, that's okay. Here we kept the period the same. Yeah, okay. But okay, what do we get as okay? This is going to be as okay, a shorter pulse duration. That's going to be considered okay, the shortest pulse duration. This is going to be as okay, the greatest pulse duration. This is going to give us the worst images, or this is going to give us the best images. Now, guys, not specifically it's okay due to the direct effect of the polarization. Okay. But indirectly. Indirectly will be as okay. The next topic. Now, we may not be able to as okay do that TD. But on the other hand, we can say it's okay. If we had a pulse, I would say it's okay. Two transducers with the same number of pulses. Let's just keep it simple. We have one transducer that produces a pulse with 3 cycles. And we can say, okay, we had another transducer also is okay producing a cycle with a pulse with 3 cycles. But if we said, okay, this transducer here at a frequency that will be high, where we can say it's okay, this other transducer here is okay, we'll have a frequency that will be low. Now, what should be able to, okay, assume from the high frequency is that you will have a shorter period for each cycle, right? Let's say that, okay, that shorter period was 0.2 microseconds. Which means, okay, gave us a frequency of 5 megahertz. Whereas, okay, as due to the low frequency, as okay, we will have a great period. We can say as okay, 0.4 microseconds. Where we, in that case, as okay, we'll have a of
2.5.
2.5 megahertz. Sorry, yeah, thank you. Yeah. Okay. Did that make sense? So what do we have here? Short period is going to just, okay, give us a shorter pulse duration. Greater period, greater pulse duration. Yeah, okay. But which is mainly going to be as okay do, because in both cases, okay, we had the same number of cycles. But it's going to be as okay directly here is okay due to the lower period and greater period, which is going to inversely have okay as so this have a high frequency. So what we mainly can say is that high frequency transducers, this one here, is ideal for diagnostic imaging. Ultra 2 is okay. Whereas low frequency transducers is or are, okay, it's less ideal. Or diagnostic imaging. Yeah. Now, I think I already gave you guys this. Okay. But please keep in mind that, of course, that's okay. There is going to be an upper limit for your frequency. Okay, it's not going to be as okay. The more as okay, we just increase. It's going to be better and better and better and better. Because good was good, but then too much good becomes bad. So it's okay. There's going to be an adverse effect of that very high frequency. Okay. Which will we, yes, okay, we'll get on to in chapter number 6, which would be a mess. Any last words of wisdom?
I just want to clarify. Basically, you can do either equation and you'll get the answer that you need, right?
Pretty much.
Okay.
But if you know the relationship, you can do the math. Or you can even, yes, okay, build up your equation. So your pulse duration, guys, is going to be the product of the number of cycles per pulse and the period. Now, when we say product, I mean that we multiply them. Clear? Okay. So, but if we just look at it in this way, okay, because that's okay, what was the pulse duration? What means okay, just the total time for which the pulse lasted. I take let's say it's okay, let's not last. Let's say that it takes the transducer to produce a pulse. And what was going to make up a pulse? 2 or more than 2 cycles. Clear? Okay, but we said okay, we had that typical range of 2 to 4, 2 to 6, or even as okay, some book says, literature may say it's okay, 2 to 10 cycles. Clear? Okay. Why not just 1 cycle? Why not 1 to 3 or 1 to 4? Because 1 cycle would just have been 1 cycle. It would not have been a pulse. Okay? Just like a person who is single, he or she is single. You won't call him or her a couple, right? There has to be as okay, another him or her, that him or her, to make it a couple or a pair. Okay, so that pair of cycles, that's going to be as okay, the minimum that you need for a pulse is going to be a pair of cycles. Okay. Again, it's okay. Why do we have an upper limit of the number of cycles is mainly going to be because that will cause the cycle to get, not cycle, sorry, pulse to get too long. Too long that it has, okay, may adversely affect your image. What feature of image that will be as okay a later chapter.
So then a shorter duration
You
will be
can
a
say
better
short,
image.
okay, let's just put it this way. Shorter pulse, better imaging, longer pulse, poor imaging. Yeah, okay. So you can put it this way and say, it's okay, shorter pulse, why? Okay, yes, that's why it's okay. There's an upper limit of how many cycles you can have in a pulse. Not just that, they also want to keep the period of each cycle at a low level. Okay, but you can say, okay, the shorter the period, the greater the frequency, right? Okay, so that's why you can say, okay, ideally speaking, it's okay, a higher frequency transducer will be ideal for diagnostic imaging because it produces a pulse with cycles of a low period. Did that make sense? Okay, guys. I don't want to start on with the next topic and just have to rush through it. So we can take that tomorrow easily, okay? Now, do you guys want to get off or you want to just, okay, study and be able to ask any questions if you have any? Either way, I don't mind.
Can you ask us questions like you did the other day? Just like, even if it's
Okay,
the relationships of things and just to like,
relationships of things, okay.
well, like just as an
But
example.
what's the relationship of you sitting here and learning
Directly.
directly? I hope that will continue. Okay, okay. So what do you want me to ask you about?
I don't like anything that we've learned so far. Just
So
to, like,
far,
make
okay.
sure we like are getting it so that when we move on.
Okay. Let me see. Sound waves or particles compress and rarefy, right? Good. When do you think you will have the greatest intensity?
During compression.
I mean, question
During compression.
during compression. Clear? Okay. So you can me says okay, that'll be as okay during which is okay, the sound will be traveling. If particles are more compressed, what would that substance be?
Solid?
Solid.
Oh.
Ah. Okay. But please keep in mind here is okay. Okay. That's not going to be as okay as you transfer solid. That's okay. It's going to go from solid to liquid, then gas, solid to liquid, then gas. Okay, okay. This compression and refraction should be taken with okay, not a grain of salt, but okay, as a big spoon of salt. Okay, because it is made as okay, it's okay, microscopic, it's okay, back and forth movement. But you can make it as okay in solids, since the particles are close to compare, okay, the distance that they move to able to just okay transfer the energy is going to be short. So it's okay, something that's going to be a shorter distance, you can do it more rapidly. Okay. Now, what is going to be the frequency of a sound wave which has a period of 5 microseconds?
Can you repeat that?
What's the period of or what's the frequency of a cycle with a period of 5 microseconds?
0.2 cycles per second. Microseconds. 0.2 microseconds.
0.2 microseconds.
Wouldn't it be hertz if it was frequency?
Okay. It will be hertz. How many hertz? Guys, the period is 0.2 microseconds.
5 hertz?
5.
5
Megahertz.
megahertz. My dear reciprocal, 0.2 multiplied by 5 is you have 5 coins of 20 cents each. Not going to be a weird coin. It's not issued yet, but if you have 5 of those coins, so how much money would you have, my dear? Five 20 coins gives you what?
100. Wait, I'm confused.
5 20-cent coins gives you what? 20 cents, not $20.
5 times 20 is 100, isn't it?
But 20 cents,
$1?
that'll be $1. I say, yes, okay, you don't have that coin yet, right? Okay. So it'll be $1. So 0.5 or 0.2 and 5 are reciprocal because the product is 1.
Yeah,
Well,
initially I said point
what will
two.
be another way of saying is okay, 0.2 is, sorry, my dear. What will be another way of saying, because 0.2, that's just writing it in as a decimal, right?
Yeah, it would be 1/5.
1/5. Did that make sense? But both of them will be reciprocal to 5. One-fifth is just writing it as a fraction. 0.2 is just as a decimal. Right. But please then keep in mind that, okay, yes, megahertz would mean millions of cycles per second. Kilohertz would mean 1,000 cycles per second. Now, how many milliseconds do you have in a microsecond? How many milliseconds do you have in a microsecond?
A 1,000? Oh no, would it be 0.001?
It'll be 0.001. A 1 or 1,000. Clear? Okay. So 1 over 1,000 of a millisecond will be equal to 1 microsecond. Okay, because a microsecond is smaller than a millisecond. Whereas if I went the other way around, yes, okay, 1,000 microseconds. You took 1,000 microseconds, put them together, they will make up 1 millisecond. Yeah. How do you think wavelength will be related to your pulse duration?
Directly.
Huh?
Directly.
Okay, good. You're right. Do you mind tell us how?
Period and wavelength are directly related.
Exactly.
I have my
Yeah.
point.
Okay, exactly. Now, how is period and propagation speed related?
Unrelated.
They're unrelated, right? Okay. How is intensity and frequency related?
Unrelated. Unrelated.
They're unrelated, right? Okay, good. Okay. How is wavelength and frequency related?
Inversely.
Inversely. Okay, good. What happens to the power? What happens to the power if the diameter of a beam is doubled?
Power doubles? Quadruples?
what happens to the power if the diameter of a beam is doubled?
Does it not change?
Nothing. The intensity will be halved. If the area doubles. But the power will be the same. Now, guys, if your amplitude increases 3 times, what's going to be the amplitude change in the power?
9 times. It would
9
increase.
times, exactly. Okay. Now, if the power is increased 10 times, if the power is increased 10 times, what is going to be the change in the intensity?
Half of that?
Isn't it just 10 times also?
Okay. Now I get confused. Now we had 2 different answers. Right? Okay, somebody said half, one said half, one said the same.
I say the same.
You'll say the same. Okay, good.
Christian, be the defining answer.
I was literally gonna ask Christian.
It is the same. Clear? Okay. It's only when you compare the change in amplitude to either of those 2 others, power and or intensity, that you square the change in amplitude to get the change in either power or intensity. Let me give you guys a written question. So now you have 2 tasks. One is going to is okay, try to answer the question, but before that, the main task is okay, is to read what I wrote. Okay. So let's put it this fancy. It's okay that the intensity of a beam is 24 watts per centimeter square. Clear? Okay. The amplitude of the waves increases to twice. What is the final intensity?
It'd be 96 watts per centimeter squared.
Yes, Krishna. Do you want to tell the guys or the girls how you got that?
Yeah, so if the amplitude is, multiplied by twice, that means it'd be 2 squared. So the let's see, the power would be multiplied by 4 times. So 24 times 4 is
Exactly.
96.
Exactly.
That was like superhuman like speed, Christian. I was like doing it and like I didn't even get a chance to finish.
That's fine. As we go through, we may see more questions like these being popped up. Okay. Now let's take one more. What's the final intensity? So what it says is, okay, the intensity of a sound wave is 6 watts per centimeter square. Now the area is tripled. What is going to be the final intensity? As the intensity of a sound is 6 watts per centimeter square. Now, if the area is tripled, what is the final intensity?
That a butterfly, Mike? Is that a butterfly?
Yes, but don't look at the butterfly. Don't look at the flowers. Just look at the question. And do you have an answer?
Is
I
it
think
18?
so. Yeah, I got 0.18 as well.
.18. How in the OMG.
I got
Point
10.8.
Okay, guys, do you guys know what it means to triple?
Yeah.
Do you want to tell me about it? Go ahead.
Can I just explain the reasoning?
No, what the reason is? What's going to be your reason?
Because intensity and area are inversely related. So if you're tripling area, isn't the inverse multiplying by a third?
It's going to be 1/3, right?
Yeah.
So 6 multiplied by 1/3 is going to be 6 divided by 3. So what's your final intensity?
Oh, 1.8.
Why
Two?
1.8? 6 divided by 3 is what? You have 6 cookies and 3 people. You. Listen, guys. Okay, just look careful here. Okay, maybe you missed this. You are mainly saying that, okay, yes, because 6 watts per centimeter, what that mean? Or centimeter square. Okay, this was 1 centimeter square. So, okay, what did we have in here? A total of 6 watts, right? Clear? The only thing that we did was that, okay, yes, we tripled the area. So, yes, okay, now it's going to be, yes, okay, 3 centimeters square. But you still only, yes, okay, got 6 watts in here. But now since the area, so yes, okay, it's going to be, yes, okay, you can either write it, again, either say, yes, okay, 6 watts for an area of 3 centimeters square. But can you, yes, okay, be further simplified into just 2 watts in each centimeter square? Did that make sense? But my dear, yes, okay, what did we do here? Yes, okay, we increased the area. So there's no way that, okay, the intensity can increase. Since we increase the areas, okay, the intensity, or yes, okay, your final intensity is going to be lesser than your initial intensity. Did that make sense?
Yeah.
Only increase the area. I didn't do anything to the power. So whether you write as, okay, 6 watts per 3 centimeters square or 2 watts per centimeter square is the same. Okay, you can even have kept, okay, as the same proportion as say about, okay, as this could have been as, okay, 60 watts and 30 centimeter squares, or 600 watts in 300 centimeter squares. If you find that's okay. Which that come out just okay, 2 watts per centimeter squared. That's fine. Look at your questions in the chapter review again. At the back, okay? But you yes, okay, if you know your relationships. Okay, yes, it should be good. Or you should be able to, that's okay. So if two things are inversely related, that's okay. If you increase one, that's okay. The other one can't increase as well. They had to decrease. But 6 watts per centimeter square just means that, okay, yes, in each centimeter square centimeter area, there's a 6 watts of energy. That becomes the intensity. That's fine. Okay, guys, so I guess I see you guys tomorrow where it's okay. Hopefully it's okay. Be able to finito this one here. Any last words of wisdom? Decide, okay, oops. That's okay. Okay, guys, I guess I will see you guys tomorrow with a new class, a new session of, okay, yes, funny topics and even crazier pictures or questions. Sorry. Have a blessed day. Take care.
See you tomorrow.
All right, see you tomorrow.
Bye bye, guys.